All right, we're going to pick up here with dilutions. Dilutions are very important. Dilutions, the volume or number of parts of the substance to be diluted in the total volume or parts of the final solution. It's also an expression of concentration that indicates the relative amount in substances in solution. So we have standard solutions that are considered working solutions. These are prepared from the stock solutions. And then we also have standards used in spectrophotometry that we were going to get really deep into in chemistry. Blank solutions. A blank solution is a solution that contains the reagents used in a procedure, but it does not contain the substance to be measured. So if you are, for example, if you're measuring glucose, but you use other reagents to measure the glucose, it's going to be a measure of everything except the glucose. So the substance measured is not included in the blank solution. Simple dilution involves two entities, and this is very important. The solute, which is the material being diluted, and the diluent, which is the medium making up the rest of the solution, usually water or buffer. So water or buffer. And the solute in the lab is usually serum. So the solute in the lab is usually serum. So why do we need to dilute? Sometimes our results can be so high that it's outside the linear range of the instrument. And that just means, like, let's use glucose again. Let's say that our chemistry analyzer can only measure glucose as low as 5 milligrams per deciliter, but only can read it as high as 800 milligrams per deciliter. So glucose, that could be the linear range of the instrument. So the instrument, the equipment. So if our glucose of a patient is 1,000, it's outside what our instrument can measure. So we would have to do a dilution. And also, another common place that we do dilutions is with the RPR or certain serology tests to determine how hot is it or how positive is it. We determine the titer. And the titer is the last dilution that shows a reaction. And we're going to talk about this more, but just remember, a titer is the last dilution where you see a reaction. For simple dilutions, there's a relationship between the solute and the diluent, and it can be expressed as a fraction. So solute, remember, which is usually serum, and diluent, which is usually water. For example, a 1 to 20 dilution, or 1/20th, contains 1 part of solute and 19 parts of diluent. So we say 1 part solute that we put into a tube, and then we put 19 parts of diluent into a test tube. So you end up with 20 total parts. So the total volume would be 20 if you were using milliliters. So example, let's say you put 1 milliliter of serum in our tube, then you added 19 milliliters of water. You have a total volume of 20, but your dilution is 1 to 20 or 1/20th, because this is the total volume. It's a little confusing. All right, so the number at the bottom, or the denominator, is the total volume. So again, we had our 1 over 1 plus 19 equals 1 over 20. So this is the total volume. The sum of the volumes in the solute. So solute, diluent. The sum is the total volume. All right, so let's look at these. And you can pause after each one. So for the dilutions, what is the dilution if you add 1 ml of solute and 4 ml of solvent? So we have our test tube. We put in 1 ml of solute, 4 ml of diluent. So we have 1 over 1 plus 4 equals 1 to 5. So our dilution is 1 to 5. So our dilution is 1 to 5, but our dilution factor is 5. So that means if we took our glucose that was over 800 and we made a 1 to 5 dilution, we would have to multiply the result by 5 to get the true glucose. And we're going to come back to that, so don't be scared. All right, so let's do the next one. Let's say we have a test tube and we add 2 ml of solute and 8 ml of solvent. So we have 2 ml of our solute over 2 ml of solute plus 8 ml of solvent. That gives us 2 over 10. And again, we do have to reduce these fractions, so a 1 to 5. So this is another way to make a 1 to 5, or you've just doubled the previous one. So the dilution is 1 to 5, and again, the dilution factor is 5. All right, so let's try the next one. So for this one, our solute is 0.5 mils, and we are adding 4.5 mils of solvent. So we're going to have 0.5 over 5.0, and this is a 1 to 10 dilution with a dilution factor of 10. So dilution for this one, 1 to 10, dilution factor equals 10. All right, when do we use dilutions? When we need to dilute samples, when we need to find a dilution factor, and we can also do serial single dilutions, which is what I've just showed you. And then there are serial dilutions. So we're going to talk about, we've talked about the use of dilution factors. We're going to go into that again, but we're going to talk about serial dilutions. So serial dilutions are a dilution and then you make another dilution. So it's the calculation of the concentration after a series of dilutions. So for example, here is our tube. We have an unknown. This is our serum, patient serum right here. We are going to pipette 1 milliliter of the patient into this tube. All right, so this is called neat, right? Or scotch on the rocks, or scotch with no rocks. It's just the serum. So that's a 1 to 1, so the concentration of undiluted serum. Now, the next set of tubes, tube 2, 3, 4, and 5, this is a serial dilution. Again, we're taking 1 milliliter from our serum and putting it in our tube, and we've added already 1 milliliter of diluent in tubes 2 through 5. So we have 1 ml of our serum in each tube plus 1 ml of our diluent. So we have 1 over 2. So the dilution in this tube is 1 to 2. Now, and the dilution factor would be 2 in this one, so dilution factor. So then they make a compound dilution, and this is a compound dilution, but serial dilutions have the same dilution factor. All right, so compound dilutions can be different. Compound equals different. And serial dilutions, same dilution factor, different dilution factor for compound dilutions. All right, so let's say we take 1 milliliter of our 1 to 2 solution, and we've already got 1 milliliter again in here, so we've made another 1 to 2 dilution. However, how can we figure out what's the dilution factor in this tube now? We have to say that tube 1 dilution factor was 2, or the dilution was 1 to 2. We made another 1 to 2, so this is now a 1 to 4 dilution, and the dilution factor is 4 for tube 3. So dilution factor, let's see, so tube 2 dilution factor is 2. Tube 3 dilution factor is 4. All right, so what about tube 4? We're going to take another 1 milliliter of our now 1 to 4, and we're going to make a 1 to 2 dilution of our 1 to 4 because we're adding 1 milliliter of our 1 to 4. We already have 1 milliliter of diluent, so we're going to say 1 to 4 times 1 to 2. So for tube 4, our dilution factor is 8. So we say 1 to 4 times 1 to 2. That is 1 to 8. So for tube 5, we are going to take 1 milliliter of our 1 to 8. We're going to make a 1 to 2. So tube 5, the dilution factor is going to be 16. Yes, 1 to 8 times 2, 1 to 16. All right, and here we go. And that's how we figure it out. So our serial dilution factor, in this case, serial dilution factor is 2. However, that's not the dilution factor for each tube. So you have to be able to figure this out, and we are going to do some more practicing of this. So this is an example of why we would need to dilute. So beta HCG, remember that's the analyte that we measure to tell if someone's pregnant or not, and we can estimate how far along they are in their pregnancy because it doubles or logarithmically increases along the way. So let's say the linear range for beta HCG is 5 to 10,000, and it's measured in international units per milliliter. So if you're doing a quantitative beta HCG, you want a number, but usually like the pregnancy tests at home or in the grocery store, those are considered qualitative. So qualitative test is just plus minus. Quantitative gives you a number. So let's say somebody needs a pregnancy test. Now, if they're not pregnant, they're not going to turn out 5, or if it's the beta HCG is 2, the machine is going to print out less than 5 milli-international units per milliliter. But let's say the machine only reads to 10,000 milli-international units per milliliter, but they're about 6 weeks pregnant. Well, we would need to do a dilution because the machine is not going to pick up anything over 10,000. And about 6 weeks pregnant, it could be between 1,000 up to almost 60,000. So this would be an example of when we needed to do a dilution. So here's the patient problem. The linear range is 5 to 5,000. Patient is 12 weeks pregnant, so we can go back and look at 12 weeks pregnant. Their beta HCG should be between 25,000 and 288,000. So what do we do? How do we get the result? We are going to make a dilution. So let's do a dilution example. Okay, so let's say, and remember, people have a big problem with this. So this came from my head. So from my head, from Dr. Wally's head. Brain, that's better. Let's say the initial result with the one-to-one sample from the patient, like neat patient sample, the machine told us greater than 5,000. Okay, so let's say we wanted to do a 1 to 10. How would we do this? So let's just say for a 1 to 10, we could take 100 microliters of patient serum, and we would add 900 microliters of diluent. Let's make sure this is a 1 to 10. So 100 over 1,000, 1 to 10. Yes. Okay, so we've made our 1 to 10 dilution with 100 microliters of serum plus 900 microliters of diluent. And we ran our sample. And again, this time, our 1 to 10 sample was 4,880. All right, now is that the result that we would turn out to the physician? No, we have to multiply it times the dilution factor, which in this case is 10. So we would say 488,000 times 10. So the patient result is 48,800, yes, milli-international units per milliliter, and because we did this dilution. Okay, and we will stop there, and we will be doing some more of this later, I